I wanted to give you a quick run through of your lesson goals. The first two were all about the SOHCAHTOA and the reciprocal functions. I've already started this problem by noticing that my theta is right here, so labeling my opposite, adjacent, and hypotenuse. I also had to do the Pythagorean theorem because the hypotenuse was not given to me. So I can't just assume that's a 30, 60, 90 or anything. I have to use the Pythagorean theorem. And I've already set up my SOHCAHTOA over here. Make sure you're writing that as sine of theta equals opposite over hypotenuse. And you'll notice that you'll have to remember the reciprocal of sine is cosecant. So this one right here looks like the reciprocal of that one right there. None of these answers is really ready to be submitted as an answer. For example, this one can be reduced to 1 over the square root of 5, which we still can't leave like that because we don't allow roots in the denominator. So that would be square root of 5 over 5 for your final answer. And so I finished rationalizing all of those and simplifying where I needed to, and I have applied the definition of sine, cosine, and tangent to define the trig ratios from that right triangle. The next lesson goal was to find your trig functions on 30, 60, 90, and 45, 45, 90 triangles. By now, you should be able to see a 30, 60, 90 triangle and just label the sides as 1, 2, square root of 3. So 1 is going to be the shortest side, 2 is actually the biggest number out of those, and the square root of 3, which is about 1.7, is sort of the medium length side, or the longer leg. Same thing on a 45, 45, 90, you should know 1, 1, square root of 2. And you should be able to easily draw both of those triangles. And because you know SOHCAHTOA, now you can use those lengths, those opposites, hypotenuses, to find the values of all of the trig functions. Even the reciprocal functions, I didn't write them down, but you should be able to find all of those. So now I've done those SOHCAHTOAs. On the 30, 60, 90, I had to switch what was opposite versus adjacent when I switched from 30 to 60 degrees, but you're really just using those triangles, making sure to rationalize the denominators when you need to. I think that only happens on a few of the ones that I had to do, but when you do the reciprocal functions, you'd also have to rationalize. So that is 30, 60, 90, and 45, 45, 90. Our next lesson goal was using angles of elevation and depression to apply trig functions to find things. And so if this mountain happened to have an angle of elevation of 11 degrees, would you know where to put that? That would be, instead of just going straight horizontal, it would have an elevation of 11 degrees. That's what an angle of elevation looks like. Had it been an angle of depression, that would have been downward. Or I suppose that would have made more sense if you were at the top of the mountain and you were looking straight out. The angle of depression would be right there. But this one's angle of elevation, and if you wanted to find out how far of a hike that was going to be to the top of the mountain, what could we do? We could use our SOHCAHTOA. So I'm hoping to find the hypotenuse from my 11 degrees. I know the opposite side, so this would be a setup for sine. Sine of 11 degrees would be the 1.5 over, and I'll call it x. And then to solve this one, I would sort of cross multiply and multiply that x over. So to solve this one, you would type in 1.5 divided by sine of 11 degrees. Make sure that your calculator is in which mode? 11 degree mode. You want to be in degree mode. And I'm getting about 7.861 miles all the way to the top of that mountain. You learn to draw angles in standard position, always having the initial side of the angle on the positive x-axis, and 200 degrees would rotate counterclockwise through quadrant 1, quadrant 2, a little past the 180 mark, right? And so that would be representative of a 200 degree angle. In radians, it works a little bit differently, right? First of all, this is a negative angle, and so for negative angles, we always start in that same position, but negative angles just rotate the other way. And the question is, how far should we rotate for a negative pi over 2? Remember that pi would have been 180 degrees. We only want to go half of that. Pi divided by 2. So pi over 2 is actually the same thing as a negative 90 degree angle. And because it was negative, I rotated clockwise, or down into quadrant 4 first. So that's graphing in standard position. We've got those terminal sides. In this case, the terminal side was in quadrant 3. Here, the terminal side was on that negative y-axis. Now, if we want to switch over and talk about coterminal angles, what's another angle that has this as the initial side and that as the terminal side? Well, we could think of this angle right here, the negative 160 degree angle. And we could figure that out by just subtracting 360. Another angle that would start on this initial side and end on this terminal side would be the one that loops around, and another 200, which you could figure out by adding another 360. So the one that loops around and adds another 360 is 560 degrees. Is that a little tougher on the radian ones for you? It might be. Just remember that each of these is a 1 pi over 2, 2 pi over 2, 3 pi over 2. So that would be a 3 pi over 2 angle, 270 degrees actually. And you could have figured that out by adding 2 pi. Or probably you would have added, with a common denominator, was 2 pi as something over 2. Is that 4 pi over 2? Right, so negative 1 pi over 2 plus 4 pi over 2 would be 3 pi over 2. Another coterminal angle that starts here and ends here is the one that loops all the way around and then comes back. So if it loops all the way around, first of all, did you notice I'm going the negative way? So that's negative 1, 2, 3, 4 pi over 2s plus another 1, so negative 5 pi over 2. And you could find that by subtracting 2 pi, or subtracting 4 pi over 2s, which would be negative 5 pi over 2. It's time to talk radians some more. We're going to convert from degrees to radians and radians to degrees. You just have to use that simple conversion factor, knowing that 180 degrees is pi radians. So if I wanted to get 130 degrees into radians, I want to cancel out the degrees. So that's how I know that the 180 goes on the bottom. Multiply straight across, that's like over 1. And then just reduce, divide by 10. And that's 130 degrees in radians. Radians to degrees, similar idea, except we want our answer to be in degrees. In this case, you can notice that the pi's cancel out. So you take 4 times 180 divided by 5, and you get 144 degrees. And a quick example of arc length and sector area. I've got this little garden drawn, and this little sector is going to be all tomato plants in here. And if we want to find like how much space is covered, then we're talking area. So the area would be 1/2 the radius squared times theta, and we can't just use 130 because that's in degrees. So we just did this one, didn't we? That comes out to 13 pi over 18 in radians. These formulas only work in radians. And so my area comes out to be 40.841, and that would be in square feet. And what would the S, the arc length, be useful for? Let's say we're putting up a fence to keep the rabbits out. How much distance is covered by that fence? So the arc length would be the radius times that theta. And that comes out to 13.614, and that's just a length, so just feet.